Well, I'll tell you what, we got ourselves a big topic tonight. You talk about a topic that the AP exam loves, and we've got it here tonight. So we're going to talk about the average value of a function on a closed interval. And I think if we really analyze the title here tonight, it's going to kind of give you a good precursor of what's to come. Now, average value, I want you to always think the y value, all right, the y coordinates of a function. Man, I can't get that A. All right. The y values, or the y coordinates, they represent the heights of the curve, aka the values of the curve. And what we're going to do is we're going to lock ourselves into a closed interval, and we're going to ask ourselves, what's the average of all the y values within this interval? Now, it is also in many textbooks, they refer to the average value as the mean value theorem for integrals. Now, the one thing I do want you to think of today when I say the mean value theorem is it is what we call an existence theorem. And maybe you remember a little talk about that. You know, we basically said, you know, that when you think of the mean value theorem that we did earlier in the year, and that was the version for derivatives, we said it proved the existence of a value c that fell within the interval a to b, and that's the key here tonight. So we're going to try to find the average height of a curve, aka the average value. Now, believe it or not, the foundation for tonight's formula that we're about to build is predicated on the fact, well, a very strange phenomenon. The phenomenon goes like this. You know, we have this curve, we'll call it f of x, and we have all the area that's bounded underneath f of x in the x-axis. Well, believe it or not, there is a magical rectangle here who possesses the same area. So the one thing you're going to continuously hear me say as we derive this formula is that the area underneath the curve and the area of the rectangle are the same. And it is the height of that rectangle, the line drawn right here. When that line intersects the curve, that intersection point marks the average value of f, believe it or not. It's a very strange phenomenon, but it's true every single time. So what I'm going to do here is I'm going to start in blue. I'm going to say the blue region is the area bounded between the curve f of x and the x-axis, and the area of the blue region is the integral from a to b of f of x dx, and that measures the exact area. All right. Now, as far as red goes, let's say red's the area of my rectangle. And I'm not going to use any calculus for this. I'm just going to go back to third grade and say, well, the area is base times height. The base has a length of b minus a. In other words, I'm going from here to here. And it's got a height of, we'll say, f of c. All right. So here's the deal. We know that those two areas have to be equal. It's almost like you took the blue region and you kind of melted it just enough so that you could reshape it, and you reshaped it into the size of that rectangle. So we know that those two things are equal. So we know, let's say, b minus a times f of c equals the integral from a to b f of x dx. All right, now the key is I want to solve for f of c. So f of c equals, and I'm going to divide the quantity b minus a over to the other side, and I'm going to choose to write it like this. I'm going to say 1 over b minus a is the coefficient, and then multiplied times this integral. And this is the formula that we're going to continuously refer back to today. This is called our average value formula. All right, and we're going to just explain a little bit here. The key that I want you to walk away with tonight is I want you to understand that f of c is a y value that happens to be the average of all the y values within the closed interval. All right, so that's our formula, and we're going to take a look at some pictures, and then we'll go practice using it. Here's just a little more, slightly more sophisticated picture to illustrate our point. We've got, starting with x equals a, we've got a ton of y values within this closed interval. Of course, theoretically, there's an infinite number of y values, and it's kind of special to think that you could consider an infinite number of y values and actually find the average of all of those. But what you'll notice is the blue line here represents the top of the rectangle, such that the area underneath the rectangle is the same as the area underneath the curve, and that horizontal line represents the average value of our function. You'll notice there a lot of parts of the curve below, then slightly above, below, and above, and you can kind of see how it all averages out. I think this slide really does a great job of summarizing the whole thing here tonight. The first thing we do have is our formula. Okay, we've got our average value formula, and then the theoretical conception here that the rectangle has the same area as the shaded region underneath the curve. And then over here, I think the picture says it nicely. We're saying that the height of the horizontal line is the average value of our function. Now, one little thing, as far as our quizzes go, when I ask you for the average value on a quiz, I like this notation. I say f and then subscript av. So f av is 1 over b minus a, integral from a to b. And I'm not sure where I saw that, but I've always used this notation for that formula, and it's always worked out nice. All right, so here's our first example. We're going to be able to sink our teeth into this formula and try it out. Now, one of my biggest pet peeves is when we don't bring common sense to the table, okay? And by that, I mean, let's take a look at this function's graph really quick. I think we could all sketch this function pretty accurately without our calculator. We've got a y-intercept of -5, of course. And then the graph opens up and increases quite quickly because of the coefficient of 3. So let's see how something like that. So we're starting at -1. And when x equals -1, I think we got a y value of -2 right there in that ballpark. And then when x equals 2, 12 minus 5 is 7, so we're up here somewhere. But anyway, that y value is 7, this y value is -2, and we're considering all of the y values within this region right here. In fact, let me thicken up that pen a little bit. Okay, we're looking at all the y values within this interval. So guess what? The maximum y value within my interval is a 7, and my y min within this interval is a 5. Or I'm sorry, I should say a -5. So what I've done is I've kind of created this interval that I know my answer has to fall within. If you try to tell me that the average value of this function is bigger than 7 or smaller than -5, then we're going to be scratching our head wondering how the heck we got that number. So let's just make sure we get something between -5 and 7. If I had to guess, I would guess maybe something in this ballpark right here is going to be the average y value. So let's go ahead and set it up. Based on the interval, we know that we could say a is -1 and b is a 2. So we'll go ahead and we'll set this up. And I'm going to say that the average value, f subscript av, is 1 over 2 minus -1, integral from -1 to 2 of the function we're finding the average of, 3x squared minus 5. All right, so let's rock and roll. We'll clean up our coefficient a little bit. And let's see, I got a coefficient of, all right, 1/3. And let's see, the antiderivative is going to be x cubed minus 5x. So we set ourselves up with a nice function here. Bounds -1 to 2. Make sure we have good notation on those bounds. Ask yourself, do I need a plus c right now? And hopefully you said no, because it's a definite integral. And I'm just going to leave the 1/3 outside. I'm going to substitute my 2, and that's going to be 8 minus 10. And then I'll substitute the -1. It's going to be -1 plus 5, which is 4. And so let's see here. I'm getting 1/3 times -6, which is going to give me -2 for the average value. So let's go back and see if that makes sense. And I think it does. It kind of put us in this neighborhood right here. And of all the y values, I think that is the average of them. Alright, same concept, slightly different approach. Instead of presenting f in terms of an equation or a function, I'm presenting f in terms of a graph here. So we're going to attack this one graphically. And we want the average value, so we're going to say f subscript av equals 1 over b minus a. Now b is a 6 and a is a -8. And my integral goes from -8 all the way up to 6 of f of x. Alright, now the difference here is we don't actually have an equation to integrate. So, in order to evaluate this integral, I'm going to rely on the concept of area. So what I want you to do is, and I'm going to kind of hit the pause button and do this here myself, is I'm going to go through and I'm going to break this graph into several different geometric shapes, and I'm going to calculate the area of each one and find the total from -8 to 6. So here we go. Here's how I broke mine up. I had -4, -2, 4 pi, and then I cut the trapezoid into a rectangle of 6 and a triangle of 3, another triangle of 1, and then a big triangle of -6. Now as I swept from left to right and I added up all those areas, Let's see, what did I get? How about 4 pi minus 2? So I'm going to say the value of that integral is 4 pi minus 2. If I counted those wrong, you're probably laughing at me and you can correct me tomorrow in class. I'm going to distribute my 1/14 through there, and it's going to be 2 pi over 7 minus 1, let's see, 7th. And so whatever this numerical value comes out to be is our average value. You know, I'm expecting it to be somewhere, you know, right in this area. So whatever these y values are, those are our average values. Here's a great multiple choice question that we've seen on the AP exam, and as you read the question, you'll notice they said on the closed interval from 1 to 5, which of the following could be the graph of a function with a property that boom, boom, boom. Now, what you'll notice is they never once used the phrase average value. They didn't whisper it or mention it at all. So the key here is as soon as you see this, there's that little calculus voice in the back of your head, and it's screaming average value. All right, so I'm looking for a graph whose average value, or you could think of it as his average height. Sometimes that helps. Sometimes the light bulb goes off when we call it average height instead of average value. I need an average height of 2. So I want you to kind of go through these functions. And they all, I know they're tough to read the graphs, but they're all scaled by 1s, if that helps. So we're going from 1 to 5, and we need an average height or an average value of 2. One of the strategies that I used was I went through and I drew a horizontal line at 2 on every graph. All right? And I asked myself, all right, first things first, is there anybody that I think I can eliminate right away? The first one that I eliminated, and I think this is a huge no-brainer, is choice C. The average value on C is, boom, 3, and that's certainly not equal to 2, so I threw that one away. The other one here that I threw away right away was D. It looked like the height started at 4 and it ended at 1, you know, and it's very linear in its behavior, so the average from 4 to 1 is about 2.5. It'd be in this neighborhood right here, so that's a little too big for what we're looking for, so I threw that one out. And then so now I'm down to 3 choices. Now, when you look at A, what you'll notice is the graph spends more time above the line y equals 2 than it does below. So I'm thinking his average value is a little bit bigger than 2. So I threw him out. And then when I got to B, just again, based on the concavity of the curve, I thought the graph spent more time below the curve, or below 2, than it did above 2. So I said the average value there is probably a little bit less than 2, so I threw him out. And then I fell in love with E. You know, it starts at 4, goes down to 0, and then back up to 4. It's very linear on both sides, so the average from 4 to 0 and 0 to 4 lands perfectly at 2, so winner, winner, chicken dinner. Now, one of the biggest bear traps that the College Board tries to throw at us is they try to confuse us on these two ideas, average value versus average rate of change. Now, average rate of change is a totally different bear. And average rate of change is your slope formula. It would be f of b minus f of a all over b minus a, aka your glorified version of your slope formula. Okay, so I brought in a couple of problems just to make sure I thought we could use the practice on average rate of change anyway, and it would just reinforce that it is a different concept than average value. And so for this particular one, I'm thinking f of 3 minus f of negative 2 all over 3 minus negative 2. And that's going to see f of 3 is going to be 0. Minus f of negative 2 is going to be a 7. And that's all divided by 5. So I'm thinking 7/5 is the average rate of change, aka the average slope over an interval. And then, let's see. Thinking, again, a little more practice with average rate of change, but now we're referring to f prime. So we're going to say f prime of 4 minus f prime of negative 2 all over 4 minus negative 2. Again, just reading the table here, f prime of 4 is going to throw us a 2. F prime of negative 2 is a 0. All over 6, so about 1/3 is the average rate of change. So let's really commit to memory here that the idea that average rate of change and average value are two totally different concepts. One of them doesn't use calculus, aka this one, and one of them does use calculus, and that's the average value today. Alright, here's a slightly different application where we are referring to a linear motion problem. We do have an object. It's traveling in a straight line. So we've just pictured this big old x-axis, and the particle has some starting position, is traveling to the right and to the left and to the right and to the left and so forth. And what they did is they did not give me the position function, but they gave me position's derivative, which is velocity. And they said, well, hey, what's the average velocity over the interval 0 to 3? So they never use the word value, but they are referring to the average value of the velocity function. They're saying this object takes on an infinite number of velocities between 0 and 3, and we just want to know the average one. So I'm going to say that velocity av, so I'm just kind of tailoring it to this problem specifically, is 1 over b minus a integral from a to b, then the function that we want to find the average of. So we can certainly do this one without the calculator. I've got a coefficient of 1/3. And you know what, I'm going to do a little bit of a u sub here. I'm going to say u equals pi times t divided by 2. Therefore, du is pi over 2 dt, which means 2 over pi times du equals dt. Alright, so let's plug it in. The new lower bound is still 0. The new upper bound is 3 pi over 2. So we're changing those bounds so that they're in terms of u. And I've got the sine of u and times 2 over pi du. Alright, so my new coefficient is 2/3 pi, kind of a squirrely rascal. The integral of sine of u is negative cosine u. Now here's a trick. We do not want to rewrite the antiderivative in terms of x because we've already adjusted the bounds, and so we need to just go ahead and plug those in. And I've got negative 2 pi, okay, let's see, that's negative 2 pi over 3. Let's see, plug in the cosine of 3 pi over 2, that's a 0, minus the cosine of 0 is going to be 1, and so I'll multiply and I'll get 2 pi over 3, and that is my average velocity over the interval 0 to 3. And the last one here today, oh, easy Bailey. As you can hear, Bailey's quite the guard dog. I don't think he could scare a fly. But anyway, we're going to, a slightly different twist here. We're going to tackle average acceleration. And again, it's just an average value formula. And I want to first of all figure out, who is the acceleration function. So we're going to take the derivative of the one we just had, and that would be pi over 2 cosine of pi t over 2. So just did a little miniature chain rule, and the average acceleration from 0 to 3 is going to be 1/3 integral from 0 to 3, and I've got this goofy function here. And what I'm going to do is I'm going to have you guys give it a whirl. Hit the pause button right now, see if you can just kind of crank it out and do the arithmetic, and come on back and see if we got the same thing. Alright, so here's what I got cooking so far. I just showed my work here. I did a little bit of a miniature u sub over here, and I solved for dt. Substituted in, you'll notice I did change my bounds here, and so forth. You'll notice I do get some favorable things to cancel out. And it looks like the antiderivative is going to be just simply sine of u. I'm going to leave it in terms of u because my bounds are already adjusted. And so then I just need to say, well, let's see, the sine of 3 pi over 2 is going to be negative 1 minus, and the sine of 0 is 0. So I've got negative 1/3 is my average acceleration over that interval, and it certainly, negative number is very viable, very realistic number. It just means, we did more time decelerating than we did, accelerating, or more time decreasing our velocity than we did increasing. So let's make sure we've got this formula down pat before we walk in tomorrow. This is certainly something that's expected to be memorized, and hopefully you can appreciate where the function came from a little bit from our earlier discussions, and just visualize the idea that there is a rectangle who has the same area as the region underneath the curve. So hope that helps, and we'll see you tomorrow.